a few bits of housekeeping. Do you guys have a class rep for me yet? You. Great. I'm glad. Great. All right. And then the last little thing just to say is I'm going to be away next week. So next week's lecture is effectively already up. I'm just going to use the 2025 one. It's not changing much. I try not to do that often, but I think for next week it just makes sense. So I will put that up on the Moodle. Well, it's already up in the Moodle. But I'll make sure it's clear on the Moodle that that one's just staying the same for this year. And then you can just watch it in the next 2 weeks. Just make sure you're keeping up, right? Cool. All right. Thanks for accommodating that. Okay. So last week we ended off speaking about how we're going to get representations of words. And the main thing to remember was the distributional hypothesis. And that said that words should have meaning based on the context we see them in. And so today we're going to now essentially do what you guys preempted last week and start to train that in a little bit more deliberately. Okay. So that's done via a method called Word2Vec. So you're going to take words and we're going to get vectors out of them. Vectors is how we represent semantic spaces. And so hopefully by the end of that, that semantic space is looking kind of really representative of the word's meaning. And we can start to do some cool kind of manipulations of words and things like that. All right. So we're starting to move towards this idea of what is it actually mean to have meaning? What is semantics? And then how do we eventually start combining it to understand large blocks of text? Okay. So here's the main idea. We need to put information about word context into word representations, and we learn word vectors by teaching them to predict their contexts. Okay. So the parameters in this case are the word vectors. So this is the one sentence that gets a bit strange. So the way these slides work is they kind of express this more in terms of a bit of probability. I'm going to explain it that way, and then I'm going to show you how it actually just maps directly onto a neural network. Okay. If you've done, you don't have to have done ASML, but if you've done backpropagation and you've done those kind of things before, this is going to start to look a little bit more familiar. On top of that, if you know what an autoencoder is, this is just a linear autoencoder. Okay, that's all this is. All right. Again, if those words are not ringing super familiar, then we'll cover it by the end of today. It's the same thing, mate. So the autoencoder architecture has the encoder block. It goes to a latent space. It goes to a decoder block. We need you to not shut out. Thank you, mate. Okay. So learn parameters are the word vectors themselves. And so all we now need to do is make sure that each vector knows about the context of its word. And so we're going to train that with backpropagation, as we saw last week. So here's the breakdown of the algorithm. We'll show kind of an example in a second. But all we're going to do is going to take that same sliding window from last week, right? And instead of now counting co-occurrences and trying to form this big matrix of, I saw the word cats and I saw the word cute together, I'm going to count how many times that happened. I'm now going to actually train this neural network, right? I'm going to show it the word cat and I'm going to show it the word cute. I'm going to make sure that they have similar representations in this latent space, okay? And by iteratively optimizing this process, so step 2, we're going to now try and say, I want them to look more similar than they did before. Because they showed up next to each other, I should slowly start to kind of wiggle out a vector space that has some like kind of meaning, right? Whether cat and cute is a closer word than cat and fire truck, okay? So let's look at how this is going to work. Should look familiar to last week, except now you can see that instead of counting, we're actually dealing directly with the probability of the words, right? So we have our central word, again, the focal word, and then we're just going to have a 2 context window on either side. And all I want to do is make sure that I think that the other words next to it are really probable when I see the word A in this case, all right? So it's given the word A in all of the cases, given the central word. What do I think is the most probable next word to see? All it's doing is predicting what comes next, or at least in this case, what comes before. Once you start moving towards actually like machine or neural network architecture is a little bit bigger, it starts to have a bit more direction. For now, it's just both directions on either side. Okay, so we're saying that A, it should then be followed by cute gray. And I'm going to train my model to predict this fact. Cute, I want it to predict gray cats. All right, so I'm going to start to train those in. And slowly, after enough examples of this, we should eventually start to form a data set that has a lot of different pairings of words, and we can use to train the model. There is one big issue immediately with what I'm showing you. Can anyone spot it yet? Yeah.
Should be a bunch of empty null value or zero or null values because lots of words won't be appearing.
So this is more in terms of the vector space. So when we were counting, yeah, then we had to have like a row for cat and then every other possible word we would have seen. And then there's a lot of empties, right? Now you're working directly with the vectors, which is why this works a little bit better. It's less sparse in that sense, right? You're getting the probability spaces. And I haven't shown you that yet. But so not quite. You are touching on an important factor that there's like an ill-defined thing at the edges of the sentence. So if I'm at the edge, then I just do 2 words to the right. And if I'm at the end of the sentence, then I just do 2 words to the left. But there's something a little bit more fundamentally contradicting about what I'm showing you. Yep.
Does that have to do with articles?
No. It actually has absolutely nothing to do with the text. It has to do with that top row of probabilities. Yeah.
Not taking into account the probability of central.
No. We don't want it predicting itself, because then you get this like feedback loop where it thinks it's doing a good job, then it will collapse. Right? Then it's just a genuine autoencoder. Okay. If I was gonna ask you guys, all right, I told you you have to predict the next word for what I'm about to say, and I said the word dog. All right, what would you predict? Dog, cat, okay.
Barked.
Dog barked. Okay, are any of those words, which one is correct? I've gotten 3 different options. Which one is correct? Well, that is the context. It's your sentence. You can say dog, cat, bird, barked. I don't know. That's maybe not following grammar, but we're not doing grammar yet. Right, so the problem here is that there's no notion of correctness in this place beside the fact that they show up nearby. And so you end up with this contradictory learning signal, because at one time I'm saying you are, let me do it on so iPad. At one point I'm saying the correct word to predict for playing is gray. And then on the next data points, I'm saying the correct word for playing is cat. And then I'm going to do it twice more. I'm going to say the correct word to predict for playing is in, and then for the. So I'm giving 4 outputs, and I'm saying, no, you just need to classify. You just need to classify the next word. Okay? And so there's this tension that's happening in how I'm training this model. I'm telling it multiple classes, and I'm asking it to pick one, but I'm telling it multiple are correct. Okay? That is fine. It's not going to break the algorithm. There's one version of this that does not do that. However, this is good, because this tension between the words is what gives us a semantic space. It's what starts to pull the words in different directions, so that now when I'm updating the word playing for cat, I'm also starting to update all the other inferences about playing and cat, right? It moves essentially my entire space to start mapping out meaning across multiple words at once. So by training one of these words, I'm actually training my entire latent space. And that tension is what allows me to kind of map it out quite precisely.
Given WT, you must say given WT, T minus 1, T plus 1, and T plus 2.
Yes. You're predicting all of them. Not at the same time. There are different data points. I'll show you now. But that is that contradicting signal, right? So there's more options than what I'm allowing you to pick. Okay? And so that is immediately going to be a weird thing. The point of Word2Vec is not to get a tiny loss. All right? That's new to kind of how we approach things. We're not here to make sure that we've optimized this to an inch of its life. We're not going to do anything like that. We are going to try and get the most out of that optimization process. But once you have the embedding space, we're done. And that embedding space will incur loss, because at some point you're just guessing at the words around it. Okay? So here's the little bit of maths that comes with this model. So we're going to be optimizing the negative log likelihood. I'm going to walk through this fairly quickly. So for each position, we have t, okay, the index of time in our sentence. All right, so the first word in our sentence will be 1, and the last word will be capital T. Okay, so all the words in some text corpus, Word2Vec predicts the context word within the M-sized window, right? And you can see M is showing up over there. So when I say you have a 2 context window, it's 2 on either side. That's just how the standard is for Word2Vec. Okay, and that's for a given central word. So here's exactly what we were just looking at with one minor change, right? I've put theta in there. Theta, all right, is the parameters of our model. Okay, does anyone want to remind me what the difference is between probability and likelihood? Yeah. Fair. In terms of this notation. So I think, okay, by this definition and then in general, I would say that the probabilities of the data. Okay. But I think what you observed was perhaps on the right track, which is I am giving you something and then you're going to use that to get the probability. So deciding on what is given that maximizes the probability, that's the likelihood. Okay, and it comes up easy in the notation. Likelihood over my parameters is the probability over my data. Okay, so you're given some parameters, you go and you check how probable the data would be produced by those parameters, by that model. And in this case, what that means is, given parameters, can my model predict the words? Okay, so prediction is probability in this case, right? And so likelihood is what's on the right, probability is what's on the left of the given, all right? So we're gonna look at some parameters theta, and we're gonna go and we're gonna say, well, if I had those parameters and I was shown a central word, how probable are the context words? Okay, and all I'm going to do is I'm going to now do the joint probability. I'm going to assume they're independent, so I don't have to do any joining of the words. It's a big weakness of this, but again, we're going to get a really big text. We're going to have a huge corpus, and so hopefully this assumption gets shaken out in that tension of having multiple predictions, but we're not doing multiple classification. I'm treating them as if each word around the context in the window is completely independent of each other. So all I'm going to do is just multiply their probabilities, okay? So for the 2 words on the left and the 2 words on the right of my central word, I'm going to look at how probable my model thinks those words are. Okay? And then I'm going to do that for all focal words. Okay? So just going back to our example, trying to map this to some notation. Okay? This sliding of the green over here, the green block, my central word, that is this product over here. Okay, these arrows coming on either side, you can see there's 2 on the right, 2 on the left. That's my M value. All right, 2 on the left, 2 on the right. And we're not taking into account the focal word. Okay, so that notation, I mean, I don't know if it looks heavy or not, but it's doing exactly what we just said in that picture before. Okay, we're measuring how likely we are to, or how probable we are to see a set of context words given the parameters we have. Okay, and we're going to try and optimize those parameters. So what does it mean to optimize it? I'm going to try and find the theta that make this probability highest. Okay, I'm going to parameterize my model in a way that makes the data most likely. And if this is still shaky to you, you can think about this in terms of a Gaussian distribution, right? Let's say I have a Gaussian and I tell you the variance is 1. So we know that I can define this. I'm an idiot. So I have one parameter to this distribution, right? Okay, theta. Let's say I have a whole bunch of data here. And it's really clumped over there. Let's give that a bump. Okay, and I start and I put my distribution here. Okay, how probable are the blue dots under that green distribution? Pretty improbable, right? They're sitting all the way to the side. They're certainly not under the mean of my distribution. Okay, so is that the likely distribution for this data? No, because the data is not probable. So what we're going to do is we're going to then optimize it. In this case, there's one parameter, which is the mean. And so we're just going to try and shift that over to the right. We become a search, and eventually we search and we find the distribution. Is this distribution more likely now? Is this the likely Gaussian to generate that data? Yep.
Why is it sum down here and multiplication up there?
Because we take the log. I'll show you that now. Okay. I want you guys to understand the difference between likelihood and probability here, right? It is a little bit subtle, but I think it's important. You'll hear it come up a lot, right? Why are we optimizing the negative log likelihood? Why the log? Because we want to optimize, because we want to have summations in our products. Why the negative? Because we want to make it an minimization, not an optimization. Okay, and then or not a maximization. And then why likelihood? Because I care about the parameters of the model, right? I care about where this green Gaussian is sitting, okay? I want to move my distribution so it makes the data I really sampled more probable. All right. So that's what we're doing here, except the parameters of our model are not the center of the mean of a Gaussian, all right? Unfortunately, it's a little bit more complicated. We have a probability distribution that depends on the parameters of my neural network. All right, the weights of my neural network, or in this case, the embedding vectors. All right, and those are the exact same things. So I'm just trying to use multiple language for whoever feels more comfortable with which wording for now. All right, I don't like optimizing likelihoods. They're probabilities. They explode and they do all sorts of silly things and they go close to zero. And if I have one unfamiliar word, now my whole probability is 0.0005 and I have to optimize that. And so it really sucks optimizing probabilities directly. All right, and by extension, likelihoods directly. And so what am I going to do instead? I'm going to log it. All right, that'll help stabilize things a little bit. Okay, and you'll see in a little bit when I define the actual, distribution at the end, the log just cancels out with an exponential, which is pretty explicitly why it becomes more stable. Okay, and then instead of maximizing, I want to minimize. That's just how machine learning works. I want to define a loss that I minimize, and so I'm just going to make it negative instead of positive here, right? Here we wanted the highest probability for the context words. Down here we want the lowest loss. Same exact thing, and then I'm just going to average over all of the focal words, and that's just by definition. That's just, again, a little bit of stability. Yeah.
It's because it's log A, because multiple, like log A B is log A plus log B.
Correct. Yes, exactly. So what happens is this product now becomes the summation, right? So again, the rule is log, let's use your words, log AB becomes log A plus log B. Okay, so all of the products of these probabilities have now been logged separately, and so the product becomes the summation. Okay, that's the identity. And then lastly, the same then is true of the product over time as well, right? This becomes a summation instead of the actual product. Okay, so again, the whole crux of this, and it's in the maths, but I do want you to make kind of clear notes of this, is that this all corresponds, right, to a massive independence assumption. Okay, I'm not saying again that cat and playing must be related, and I'm not training it with that in mind. The context window is treated completely separately, and also all of the separate words, playing, in, cat, they're all treated separately as well. All right, I'm not trying to do anything clever about, I saw cat last time, so now I'm going to take into account and not optimize it as much. It's all, everything is completely separate, and I'm just going to try and pull two words together. Okay, it's a really, really, really unnatural thing to do. But this is the foundation of essentially all of our intuition in NLP, which is the fact that if I do a really silly thing really, really quickly and very, very often, I probably end up with something that works. Transformers are not that smart. You will see. They're very close to this. And they're doing silly things. They're just pattern matching over and over and over. The reason transformers have made such a big difference is the fact that you can optimize it significantly faster than anything else we've seen before. And so I can show it lots and lots and lots of data. Okay, and eventually the data constrains the problem. Okay, so now how are we calculating this probability, right? So I've been leaving that out while we do the definition of the loss, but we now have a loss function. Now we just need to go and take our words and define the probabilities of them. Okay, so for every word, we will have two vectors for it. So we'll have it, the word cat being used as the central word, and we'll have the word cat being used as the context word. All right, and again, this is why we don't predict cat from cat. We don't want that to start pulling these two things together. Cat when it's in context and cat when it's the focal word should be represented as two different things. Okay. What happens is then the context words will get pulled by a whole different, every update pulls the context words, and that will start to guide the other words to where they need to be in the latent space, right? They become this implicit learning signal for each of them. All right. So once the vectors are trained, usually you just throw away the context vectors and we just only hang on to the focal words, and those become our embeddings. Okay, and I'm going to use that word a lot today. So these are embeddings. This is also the parameters of our model. So by moving these two vectors to be closer to each other, you're optimizing those parameters theta. That's what we're given, right? We are given the representation of our words, and we are asked if these were the representations of our words, and we think that words follow this distributional hypothesis, will I see cat and cute together? That's what we're asking, right? Here's my dictionary of meanings, parameters. How probable is it that cat and cute will be together? We're going to try and pull those together, and eventually we'll just come to the conclusion that they are supposed to be close together. All right, if you like cats. And then in that case, we throw away what's remaining, and we just have these embeddings, which again are the parameters of our model. Okay, so for a central word and the context word, the probability over the context is the following. So what we do is take the dot product between our focal word and the current context word we want to predict. And then you just say, what about every other word in our vocabulary, right? All right, so you're normalizing over the entire vocabulary, and you get this probability distribution. So W is an element of capital V being our vocabulary. And then all we're doing is summing over that, and you divide. What is this called? This is the softmax function, okay? It is the simplest way of getting a probability distribution, all right? And so how do we think about these things in the middle here? Okay, so I have an example. I like to talk about this. Let's say I have a jar on my desk here, and it's full of red balls and blue balls, all right? And there's 4 red balls, 6 blue balls, and I shook it up, and you don't know the order I threw it in. You can, ignore all other reasonable information you might bring to this problem. So that's the jar, all right? What is the probability of me pulling a red ball from that jar? I'm definitely not giving you guys the answer to this one. There we go. What did you just do, right? You took the value you wanted, so red balls, you counted it at the top, you divided by the total. What did we just do? We took the value we care about at the top, and we divided it by the total. All right, in this case, the total is all of my vocabulary. So that's step 1, but that still looks a bit weird. So what are we doing here that we're not doing in the red ball, blue ball example, right? So, yes. Bye.
Space of C, like thinking with references.
Yep. Okay, so the like kind of values that we're actually working are a little bit harder to define. Okay, so let me put it this way, right? So that example was easy because I had real things, right? They were just natural numbers going positive. Those are called the values I gave you were called propensities. All right, I apologize for my screens. I don't know why they're doing that. I hope it's not happening here. So when you said the probability of red was 4 divided by 10, all right, what you had done is you took the propensity of red and divided by the sum of the propensities. Okay, that's a bit of a weird word. I don't know if you've seen it, heard it before. I like it because it makes a clear distinction. The thing about propensity is it's for me to define, and they usually don't really matter to the problem. So if I made my jar bigger and I put 40 red balls, 60 blue balls, the probability stays the same. All right, but the propensity is now 10 times larger. We are the ones who get to define propensities for our problems, okay? And so what I am doing here is defining a propensity, okay? It is a different propensity that's for me to say, all right? And there's going to be a very important point that comes a little bit later in the lecture that understands that point. So keep this in mind, that propensity is for me to define, okay? So what have we done? Why the exponential? Well, let's say I had a cat-dog classifier. So not red ball, blue ball. I'm showing you pictures of cats and I'm showing you pictures of dogs, right? If I hold up a picture of a dog here and I ask you, is this a dog? Hopefully you're all going to say yes, right? Okay, I'm going to take that for granted. If I hold up a picture of a dog here and I said, is this a cat? What are you going to say?
Yes.
Yeah. All right, what are you going to say if you're not trying to, break my example? You're going to say no, right? What you didn't say was 0. Okay, you said, no, that's definitely not a dog. You were in the negative, right? And what happens when I now try and sum when my propensity is positive and negative, right? Let's say dog propensity is 5, cat propensity is -2. If I'm going to go for a probability now of dog, it's 5 divided by 5 minus 2, 5 over 3. That's not a probability. That's greater than 1, right? It's ill-defined the minute you get negatives. So I have to change how I'm phrasing my problem. If I want my model to know not just that a dog is a dog, but that it's not a cat, which is what I want my model here to say, cat is cute. It's not a chainsaw, right? I'm not, I want the negatives. So what I have to do, I have to find a way to map those representations into the space of positives, which is what the exponential does. Okay, my exponential function is defined between 0 and upwards to infinity. Okay, and so we just use the exponential to solve that problem of negative propensities. And so now I am free to take this dot product. Okay, the last thing we need to try and unpack here. What does the dot product tell us? And I'm going to draw some vectors and you can tell me what's going on with the dot product. Dot product, large or small? Large. Okay, very true. Okay, dot product, large or small? Well, negative, right? Large negative value. Why? Because it's pointing in the opposite direction. And then lastly, let's take this away. Small, right? They're orthogonal, they're 90 degrees, so dot product's going to be close to 0. Is everyone comfortable with this idea? Right? I don't want to bore you guys, but I do just want to make sure I'm not leaving anyone behind here. We build off of these embeddings pretty much the entire class, the semester. Okay. So what did we just do? Well, again, I don't know how to define similarity, but I know how to define if vectors are similar. It's the dot product. So I'm going to go down my list of vocabulary. Okay. I'm going to just take the dot product. I'm going to say those two words in my real data came close to each other. So their dot products must be large. Okay. I want that to be high. And then the problem with dot products is they could be negative. So I'm going to have to exponential it. And then again, now I have my propensity. Exponential dot product of the vectors is the propensity of this problem. It's for me to define. You can go give your own version if you want. If you do and it makes a breakthrough, we'll write a paper. It'll be great. And then all I have to do now is to go to a probability, right? Take the propensity of what I care about, divide by the sum of the total or the total propensity. Right? And that is again over my entire dictionary. So what I'm saying is I want the dot product for the two words I'm currently seeing to be larger than the dot product of any other word in my vocabulary. All right, that's going to push up my probability. Does that make sense to everyone? Correct. All right, and that's only going to happen when I am aligning the vectors for the words that show up close to each other. Okay. So let's get our bearings again. I know we're doing a lot of defining and a lot of manipulations and stuff. But what did we start with? We started with a distributional hypothesis. Now I've only really gone 3 slides ahead. So you can see we're not actually moving that quick. We started with the distributional hypothesis. We knew what we wanted. We wanted to define those probabilities. We made our loss function, and then we just made some easy assumptions about the independence of it so that we can just churn over it quite quickly. Okay? I want to have word vectors that are highly likely, so I defined a loss over those word vectors. Okay, I have to define the probability properly so I can slot it into my loss at least. So there we go. We defined the softmax function, and we're going to be using that as we go ahead. Okay, we define the propensities to plug into that softmax function. And so now we're just going to actually go and train that method. All right. And I'll show you the update rule in a second. But again, all we're going to do is say, well, I saw the word A. I'm going to now go into my context embeddings. I'm going to take the dot product with A. I saw cute and gray. We're going to try and push those probabilities up. I'm going to repeat it for cute. A saw cat gray, gets pushed up. And eventually, by pushing up all of these probabilities, we should hopefully start to pull words together. Okay? And this is where I'm going to do one more detour, which is I'm going to try and explain how this looks when it's a neural network. Okay? Because what we're seeing now is just the fact that I am taking this vector and I'm taking that vector and I'm dot producting them together, right? All right, plug that into the exponential, all that stuff. How does this map onto our current intuition of a neural network? So, yeah. It's going to be the output of my neural network. No, that's what we optimize. I want that number to go high. If I'm giving it that number and I want to, that's not exactly fitting the problem, right? So there is one important distinction that I want you to again be aware of, and this is the kind of thing that trips you up because they're named different things in PyTorch. So this linear layer, it's also sometimes called the dense layer, depending on which library you use or whatever. So that is just a matrix multiplication, right? So if I have let's say dense layer, okay, I'm going to have some input neurons. That's going to go to a set of next neurons, right? Sorry, I write my neural networks from right to left for good reason, but maybe not for today. Okay, so we have an input to my neural network X, and we're going to go to some hidden layer H, all right? No activation function on H yet. We're going to leave that off for now, all right? And so what's happening here is we have our weight matrix. Let's put my weights in blue. Okay, and we had W times by X is equal to H. Oh, we're all comfortable with what I just drew on the board, right? Yeah, I don't want to assume everyone here knows machine learning, but we're all happy with what a linear layer is in a neural network. Cool. Now, what happens when X is 1 hot? Okay, so I'm going to go down that X value, and I'm just going to have a bunch of zeros. So this is going to be 0, 0, 0, 0, 0. And then we're going to get my 1 over there, 0. Okay, what happens to the weight matrix? That's a hard question, but let's try and work through it. What is H? Can you tell me what H is going to be if, let's say that this is index, let's say I is equal to K.
All the weights except I is equal to K, it's not going to change, all is going to become 0. Well,
correct. What does that mean? What is that? What is the exact representation of H? I is an index. You're really close, dude. You're super close. No. Think about it. Think about the matrix multiplication, right? Think about how this is going to map onto there. Only one of those indices is 1.
It'll be a matrix with a bunch of zeros and a 1 and I, and index I.
We're talking about H.
Yeah, but which node in H?
All of them. Anyone else want to have a guess? While you keep thinking. Anyone else want to have a guess? It's a hint. Okay, here's a hint. Explain it to me in terms of W. Yeah. Correct. There we go. Sorry, you were close when you said it's I. So let's look at what happens with dot products, right? Okay, if I just have this vector A, B, and then this is 0, 1. So we have that 1 hot, right? What's the dot product here? It's B, right? Correct? Everybody comfortable with me there? Okay, if I then make this a matrix instead of just A, B. Okay, so A, B, C, D. What's the output? Yeah, there we go. So what just happened, right? The 1 was in the second index, and so I extracted the second column of my matrix. Okay, and again, I sometimes like doing this example. If I think about a matrix as a vector of vectors, right, then this is just V1, this is V2, this is V3, this is V4. Okay, and you have the lines on top showing that those are the vectors 0, 0, 1, 0. Okay, think of it in terms of dot products, right? I'm just going to do it with my hand. Sorry, guys, online. You're going to take those 4 values, you're going to multiply it there, you're going to sum up the output. V1 times by 0 is 0. V2 times by 0 is 0. V3 times by 1 is V3. V4 times by 0 is 0. Okay? And so again, I mean, I know I wax lyrical about this, but maths is about framing problems in ways that make it easy to understand. If you want to understand, if you're in an exam, let's say, and I may ask this, if you're in an exam and you're wondering, damn, what's the relationship between the dot product of with a one-hot input and an embedding layer? Well, just draw it this way. Draw the matrix as a vector of vectors and then just do the dot product. And so we will get V3. All right. I swear to God, when I think of this problem, I still think of it this way. I still have to map onto this because it's hard thinking about one-hots and multiplications and all that stuff, right? No one's that good at mental math that I've ever met. Everybody's framing it in a way that makes it easy. Okay, so I'm going to put you guys under pressure again. So this is our dense neural network with a one-hot input. What is dumb about this? You can already see it starting to happen here. There we go. It's very, very wasteful to go and now have a one-hot input when my vocabulary is 1 million, right? Or however many words there are in the English dictionary. All right, what can I just do instead? Again, what's the absolute dumbest thing I could do to represent that one-hot vector in a really efficient way? Yeah.
Just whatever is that value at the I index, just put it there instead. Just say the matrix multiplied by scalar value.
I think you were close to the first time. Slow down, backtrack. What can I do?
If it's just replacing that.
Yeah, how can I represent this vector more efficiently?
Like I said, you
just store the index, right?
Yeah.
There we go. So instead of having this giant one-hot vector, all I have to do now is store the index where the 1 would be. Okay? And so now instead of having 0, 0, 0, 0 and on the 20th index, I just have the number 20. Okay? This becomes useful because instead of representing things like a sentence as 0, 0, 0, 1, 0, 0, 1, 0, you get the point. All I have to do here now is erase that nonsense. And I have my sentence, which is 23, 12, 2. Right? Same story. So it becomes far more efficient to represent that. The difference is now that you don't do matrix multiplication in the same way. All we're going to go and do is take that W matrix and extract the ith column from it. Okay? That's all the embedding does. Yeah.
I wanted to ask, you said we would store the whole sentence as that list, but would it be the sentence or would it be like our snippet where it's like the context in our vocal word?
So it depends on the model. It depends on the model. So maybe don't worry about that for now. Let's just stick to the vectors, the individual vectors. So one hot vector. Okay. So what have we done? All right, we have found that W times by X is the same as just indexing. Make sure I do this properly. Into I. All right, when X is a one-hot vector where the 1 is at index I. Okay, same exact thing. And that's what this is using. That's what Word2Vec is based on. If I use the indexing version, it's called an embedding layer. If I use the one-hot vectors, it's called just a dense layer. Okay, so how do we think about what we've been doing up to now when what's been happening is we've been indexing into these 2 matrices. I'm taking 2 embedding layers and producting them out, right, and then passing that into a probability distribution. That can be reframed into a neural network as the following. I can now draw this neatly. Right. I'm going to have my input set of neurons. Okay, that's X, and I'm going to put the I just to remind us that that's where the 1 hot is. That's not my ith data point. Okay, I'm going to have my weight matrix coming in here. Okay, and again, that's an embedding layer. So that's now going to just extract some kind of representation from my weights. And that should be the representation for that ith word. I'm then going to have another layer. All right, so no activation function. Mapping back out to the same number of neurons. Okay, back over my dictionary. And all I'm going to try and say is that now this output must go through a softmax distribution, right? The same exact way you've done every classification problem that you've ever had in machine learning. You run it through a softmax at the end. And so now you're classifying over your context variables. Okay, and it's still 1 hot here. That's going to be my yi. All right, they will be at different places because this is my focal word, my center word. And then this is my context word. Mathematically, these are the exact same things, right? It's the exact same thing as saying I have 2 embedding layers being producted to be equal to each other in the middle, and as saying I have a forward pass through my neural network where I have to predict the context word from the focal word. And this is why I said it's like an autoencoder. It's not an exact autoencoder because I am predicting a different word, but it's mapping onto the exact same dimension on the output. And then what you will notice, again, if you've worked with autoencoders, is that this is our latent space, right? That's always this compression that we want to do to get meaning out of data. There it is, all right? So all Word2Vec, if it is helpful to you to think of in this way, it is just like an autoencoder, not exactly, you're predicting the context words, but it is like an autoencoder that has no activation function. So linear autoencoder over my dictionary. And you can see the foundations again. Hopefully for most of you in your research projects, you're working with something like a transformer, you're working with something like a variational autoencoder, right? You've probably seen these models somewhere at least. You can see how the foundational this was. This was in 2013, right? Pretty cool, I would say. Like a linear autoencoder, because you're going from focal word to context word. But you're still classifying over your dictionary, right? So that's where the softmax comes in the architecture. All right, I see we have 2 minutes, and then I'll take a break, and I know that was a lot of information. Next lecture will be a lot softer, not as in the next 45 minutes after this. Okay, so let's recall that parameters are theta. Again, that should hopefully be, we have another framing of the problem that makes it a little bit more machine learning-y. So it's the weights of my neural network. These vectors are learned by optimizing the training objective just with straight gradient descent, all right? So we had our loss function. It's the negative log likelihood. We can write it at the bottom here again. Okay, and then all we're going to do is say, well, that negative log, I'm substituting in my dictionary. And so in that case, this is actually just the same way as saying take the loss on these individual data points and sum that loss objective over each of them. And then all I'm going to do is just optimize that with gradient descent. Okay, and so for the center word, the loss contains this distinct term for each of the context words. And so this lets us look in more. And so then this lets us now go and optimize each word pairing separately. Okay, these are wordy now. So with the central word cat and the 4 context words, we can then, since we are going to look at just one step, we will pick only one of the context words for each. Let's say cute. Then the last term for the central word cat and the context word is the following. Okay, so the previous slide said that we can do each of these separately. All right, it's just the overall loss in my batch is just the sum of each individual pairing. We kind of derived that earlier from the independence assumption in the probabilities distribution, but it makes computation really easy here. Okay, and so what are we doing? We're taking the vector representation for cat. All right, that's the input. Taking the vector representation for cute. Dot product, exponential, there's my propensity, and then I just divide by the entire propensity, the sum of all propensities, right? That's now given me a probability of cat and cute co-occurring, and then that probability, I want to make it stable and make it a minimization problem, so negative log, and then that gives us all of this, right? And again, you can see that what happened with the log is that it canceled with the exponentials as we predicted earlier, okay? So the log splits the fraction, that's why it becomes that. the negative over there is the negative here, and then the negative times by negative gives you positive. So a little bit of arithmetic, but really it just splits this into something that's quite stable. And all we're going to now do is say, I want the dot product to be high between the two words, and then I want the log sum exponential of all other vectors to be low. And again, if you've used PyTorch and stuff recently, you will hopefully have seen the what I think it's even in NumPy. I think it's np.log sum x, and you've probably looked at that and said, what's going on there? I mean, maybe Gemini just did it, and we were like, sweet, I'm going to take it. And that's fair too, but now at least you can see where it's coming from, right? It's literally log sum x in the function itself. Okay. So note which parameters are present at the step. You have the central words parameters. So one index for our one embedding is coming through on the input side, on the encoder side, and then we have multiple parameters, all of the context coming through on the output, right? So all of these layers are now trying to then predict what the next word is going to be. All right, they're all going to be used. And so here is the full process, right? You extract from your embeddings, your context and your focal word, you dot product, you take the exponential, and then you do that for all of them, right? You keep track of which one you care about, but I need to be able to divide by the summation of my propensities. So I do that for all of them, and then I just plug it straight into my loss for that one data point. Okay, and then after that, you then just come along and you do gradient descent. Right, so we're not going to derive that. You just backprop in PyTorch, and so you get the derivative of your loss with respect to cat, and you get the derivative of your loss with respect to all of the context words, so all of the decoder. Okay. And you just go and you update your parameters for every data point over and over and over. There is one more thing that I want us to notice about this that's going to be a little bit annoying is that efficient to redo this dot product every single time and then do the summation? Is that actually a nice thing to do? No, you're summing over a vocabulary? Yeah.
Why don't you just do it once, store it somewhere?
No, because they're changing them. Every single time I do a gradient descent update, that thing changes. All right, and then hopefully that's pushing all of my weights to change.
Then can you store like a separate value which shows which one changed? And some might not change, you just only change the sum for the one.
So all of your context variables are getting some derivative, right? It's possible, especially towards the end of training, that they are actually orthogonalizing and they're sitting in this high dimensional space and stuff. But all of your context weights are actually getting some attribution there. So they're all competing to be mapped onto by cat, right? Like every word in your decoder wants to be activated by cat, let's say. And so, no, that's you're on the right track, but that is a little bit that's essentially, I would say, momentum, right? Like if you know Nesterov momentum, that is to a degree like using Nesterov momentum, but that can only last you so long, right? That can't be your only gradient. Okay, so we'll discuss how we fix this. Let's have a bit of a break, and then we'll wrap off with the softer stuff.
What related to the course work and more just models in general,
Yeah.
bits in general.
Yeah.
I've just got a form on trading.
Sorry, let me mute this quickly. Alrighty, guys online, can you hear me all right? Great, thank you. So what's the
So I need to take notes and go back and watch it again.
That's the idea. Okay, cool. All right, so let's just recap quickly what's going on here. So by making an update to minimize this loss for one pair of words, we force the parameters to increase the dot product between the focal word, which is cats, and the one context word we currently care about, which in this case would be cute. So now our model is learning that cats are cute. And at the same time, we want to decrease the similarity between the word cat and all other words in our vocabulary, right? Coming from the fact that we have this positive sum, well, log sum over here, and we're trying to minimize, so we want to bring that sum down, which does lead to one little weird point, which is the fact that when we're summing over our vocabulary, we're not excluding cute, right? So there is this pressure to make the dot product the same for cat and cute, and then this minor pressure here to make the dot product dissimilar for cat and cute, okay? But that just comes out essentially in the wash, right? The way to optimize this is that because that one value of that negative for cat is sitting in the numerator, it's going to be dominated over the little bit of pressure to make the embeddings different in the denominator, okay? So that is a little bit of a, weird oddity, but since you're making updates for each context word and all the central words in your text, on average, this will work out to give you the right embeddings, okay? So again, we're not going to always make the completely perfect choice. We could make some kind of exception there if we wanted to, but we actually just don't care, right? It's going to come out in the averages, and eventually, because this is essentially a classification problem, we have to pick one of these words from our vocabulary, and so you're going to end up trying to just pick the right one. Okay, but that is just a thing to note. If you're ever, going over that equation, you're like, oh, wait, that's a little bit contradictory. It is. Okay, so why is this extremely inefficient? Well, you guys have preempted it. You have to sum over your entire vocabulary every single time, right? So you don't want to have to do this because now you have to go through the dictionary plus one vectors, right? This is still Word2Vec. Okay. So what we're going to do instead is we're just going to pick a subset of the other words, okay, and make sure we decrease those, and we make sure we're not picking the words that are meant to be the ones we're classifying. So we just pick any of the other ones that are not in the context window, and we pull those down. All right, so we randomly select K words, not the cat as cute one, and then that becomes now what gets filtered in through that log sum exp. Okay, very simple idea, nothing too intricate there. There is one difference though in how the math works out, which I'll show you in a second. But ideally, all we're going to do is say, I'm not going to do this for every single word in my dictionary. I have more than enough data points, right? How many word pairs can you get from Wikipedia? Well, with every focal word, I'm getting 4 word pairs. And how many focal words in a Wikipedia page? A couple thousand at least. So I have thousands of data points. And so now I can actually start to shake out this kind of distribution. So all I actually care about is just picking K samples, and I trust that, again, it will come out in the average. What matters most here is the fact that I'm optimizing cat and cute and minimizing some of the others, right? Minimizing that dot product. Okay. And so now we can return to that update equation then. So as before, you're going to increase the similarity between cat and cute. But now we decrease similarity between the cat and the context vectors, but not all of them. All right, but only with a subset of the k negative examples. Okay, and so since you have a large corpus on average of all updates, we will still update the vectors sufficiently many times. Okay, so formally the new loss is as follows. So it's the same exact thing. You will notice that that has changed a bit. And then it's this term over here. You'll notice that that's also now got this sigmoid in it. Okay, so in this case, the wi through k are the k negative examples chosen at this step. And then this sigmoid here is then obviously the sigmoid function. Okay, so why have we switched to a sigmoid function and what's actually going on here? There is an equivalence between a softmax classification and a sigmoid classification. Have any of you seen that before? Right? Wait, you have? So you, yeah, okay, cool. So I can go through this quite quickly. So there's a mapping from a softmax distribution. When you have two classes, you can go from softmax to a sigmoid distribution, okay? And so this is essentially what we're going to do. Instead of doing now this big multi-class classification of our entire dictionary, we're going to do multiple binary decisions, okay? Is cat and cute going to go together? We're optimizing that with a sigmoid. So that's now a yes or a no. On this side, we're now going to do the same thing. Is cat and other focal word meant to go together? We're going to optimize them, and we need to pull those down. Okay, that's why now we have the negative inside of the sigmoid. Okay, we want to make them dissimilar. Okay, and so then I wrote the note there. So just it was before it was the multi-class, now it is multiple two-class or binary decisions. And then I wrote that derivation on the third last slide. But if you've all seen it, then we don't have to do too much of that. But it's good just to jog your memory. Okay, so we're now going to say, well, I have a subset, so I can't do the same multi-class classification. That is going to be a little bit misleading. So instead, what I want to do is I want to do a multiple logistic regressions, sigmoid classifications. And then I'm going to do all of those multiple ones. I'm going to say either the word must be similar. The focal and the context word I care about must be similar. And then all others in my negative sampling, just the subset that I grabbed from my vocabulary, they must be dissimilar. Okay, and that is then the canonical version of Word2Vec, right? You do the logistic regressions, but again, that just comes from the fact that we were previously doing softmax, and then you do negative sampling. So again, we can churn through this a little bit faster, right? We want to do as many focal word updates as possible. Okay, then there's two versions of Word2Vec, depending on what's your input, what's your output. So I've been talking about skipgram. So skipgram is the version on the left, where I give you a focal word, you predict the context. Then there is continuous bag of words, or SIBO, where I give you 4 context words that get summed together, and then that needs to predict cat. All right. So from the sum of my context vectors, I need to predict the central word. It's the same type of idea. I lean on skipgram a little bit more because, again, I think that tension between the different classifications is actually what gives you a good latent space, but both will work. There's one issue with the sum here on the right-hand side, which is the fact that the sum loses ordering in your words. Obviously, in this case, we weren't treating the ordering anyway. We had that summation over all the contexts, so it doesn't really matter. But there is kind of ways that that sum can kind of collapse a little bit of information. Whereas by going from cat to in, cat to cute, cat to gray, cat to playing, you can now start to actually get very precise mappings. Okay, but when I have the sum here, we don't know whether or not we're getting great representations for all 4 of those separately at that update, right? There is a what's the word? Damn, I've gone blank on the word for it. It's an attribution. There's a different word for it, but it's the attribution problem, right? I can predict the context for cat from the sum. That could be because I have an exceptional representation for playing and absolutely no good representation for cute, but I'm still able to just rely on the one context that I now have a good representation for. I'll try to remember the actual word, but it's essentially an attribution problem. RL loves talking about this because you have to attribute the reward backwards through time. It'll come to me if I stop trying so hard. Okay, but then just know that there's a problem with continuous bag of words. There's a potential weakness where one context representations can dominate that sum, and then that's what gives you a good prediction. Whereas skipgram, you're forcing it to have good representations for each individually. There's trade-offs. This is a little bit longer and harder to learn. This can get you good results, but you know, not necessarily the optimal one. Okay, then if you're trying to kind of close the loop, or you're thinking of ways that you can do cool things with this, people have gone and used the stuff we spoke about last week, which is counting-based methods, and augmented it with this kind of vector-based method. And so what they would do is get glove, right? So that's both counting and vector-based. Essentially what it is, you take the word count matrix from last week and you regularize it by weighting the count similarity by the dot product of your vectors. Okay, so now you get this weighted counting by your vector dot product, but it's still a global corpus thing because you have that giant count matrix. All right, we're not going to go too much into it. I don't think that really informs current models as much as just vanilla embedding layers. Okay, so that's how you get an embedding, right? A lot of like mechanics to it, but fundamentally, you take a neural network, you show it a focal word, you ask it to predict 4 of your context words separately, so it's 4 different data points. You do that for multiple context words, and eventually gradient descent will give you that encoding layer, which in our case becomes what we call embeddings. Okay, those embeddings are vectors that now represent the words. But we don't know yet. Okay, I've told you they represent the words. Let's see what happens. Okay, and so a big aspect of this class, NLP in the modern day, and I think the people who are good at this are the kind of people who can also like walk into a company and make a big difference, is how you actually evaluate these models, right? So there's 2 types, extrinsic and intrinsic evaluation. Okay, so intrinsic evaluation is when you do your evaluations based on just the internal properties of the model. All right, it looks at the internal embeddings and how well they capture meaning. Okay, and how can you do that? Well, you can take your embedding layer now. So again, the encoder of this Word2Vec, and you can just treat it like a lookup table and start to probe things you think should be true, right? You're just designing this experiment now on these word vectors. So you can do things like make analogies or look at word similarity. Okay, and I'll show you some examples now. The other one is intrinsic evaluation. So that's when you do it on a real task. All right, so this is when you do a downstream evaluation on the embeddings. And your idea is that if you have good embeddings, you should be better at the downstream task. Okay, so that's usually when you go and have some kind of like prediction model off of the top of your embeddings. Maybe you want to fine tune them, maybe use them as another layer, and so on. And we will talk about transfer learning and stuff like that towards the back end of this class or this, lecture series. Okay, and so in this case, you'll often train the model several times over, making different choices potentially, and see which one gives you the best downstream performance on some kind of actual task that you care about. But importantly, for it to be extrinsic evaluation and not just like inference, it has to be a new task. Okay, so I trained my Word2Vec, I take those embeddings, and now I classify whether those words are nouns. Right, that's extrinsic evaluation, and that's called parts of speech classification. One thing to note about vectors in general and embeddings, and this is kind of foundational to actually most things. If I can predict something from a vector, it means that vector encodes it. Okay, and it's obvious when you say it in words, but it's crazy how many times you could actually just gain insights to what's going on by just taking a bunch of vectors and trying to predict something from it. Okay, for example, if I train my Word2Vec model and I try and predict if it's a noun or a verb, nothing about how I've trained it has made it do that, right? Nothing has said that this should learn its parts of speech. So now it's open question, right? Can I just take that vector representation for the word cat and predict that that's a noun? Can I take the vector representation for the word run, predict that it's a verb, right? And that's its own classification. You do that over your entire dictionary, and now you can start to say, does my embedding space understand parts of speech? Yeah.
So you're saying something vector representation and that vector is encoded.
Encodes that information. Yeah. Okay, so that's one thing to maybe also just keep in mind, because that it comes up in subtle ways as we go. But you end up probing. Usually it's called probing. You probe the vector. Okay, so pros and cons of this. Intrinsic evaluation is usually really fast, but it doesn't tell you what's actually practically useful. Extrinsic evaluation, it tells you what's better, but it can rely on you training multiple models to do multiple different classification tasks. And so it's usually a little bit more laborsome. the thing that made Word2Vec famous, and if you ever want to like get into a discussion about Word2Vec with someone or embeddings with someone, they will bring this up, is what they showed is that you can do essentially logic problems in a Word2Vec latent space. All right. And so if I took, for example, the vector embedding for king, all right, in my embedding, I just went and got that index for king. I subtracted the vector representation for man, added the vector representation for woman. You got back to approximately the same vector representation for queen. Okay, and the way they did that is they just did those operations, they added and subtracted vectors, and they went back to their dictionary and looked for the closest vector to what they got out, and the closest one they got out was queen. Okay, so what does this mean? It means that this is actually encoding aspects like royalty, aspects like gender, and so it's starting to understand and form that semantic space. And this is why we call embeddings semantic space, because those are semantic concepts, right? Not to kind of care too much or put too much emphasis on what those semantics are, that comes from the data, right? So it depends. If you show it Wikipedia, it will start to develop a semantic space of whatever those Wikipedia pages we're talking about, right? And then you can also do syntax, okay? So if I take the representation for kings minus king plus queen, I get back to queens. And so what was left by this operation here is essentially a vector representation for plurality. Okay, which is not something I can train, right? I can't go and show language of a broad notion of plurality. I can show examples. I can have a vector representation for kings and king, and hopefully the context for king and kings is slightly different, so that gets me to an ability to make those slight distinctions, but it's going to be subtle. But if I have sufficient data, that will start to shake out. And so now I can take a single word, queen, and I can make it plural with my plurality vector. And again, so this is the foundation of where we start talking about semantic spaces. You can do operations which reveal the fact that there's more than just a knowledge of the words. It's actually an understanding of concepts that you cannot really define easily, or you cannot show with a single data point. It is a semantic. Okay, and so they also then went and looked at like pairs of words. So this is all intrinsic evaluation. So the distance from man to woman, from uncle to aunt, and king to queen is all roughly the same distance, and they're all pointed in the same direction. And then you have that arithmetic for the kings and queens at the bottom there. So again, your vector space is starting to encode concepts rather than just entities. Right. Word2Vec has a cool property where it can know the capitals of countries. So for example, the distance from China to Beijing, Russia to Moscow, so on, they're all roughly the same direction, not perfect, roughly the same direction, and then they are roughly the same magnitude apart, okay? And so this axis here is essentially giving you the semantic notion of a fact that a country has a capital city, all right? So you can see it does get a little bit confused sometimes with things like Rome and Athens and so on. Okay, then glove. All right, again, a mixed counting based method can do things like slow, slower, slowest, short, shorter, shortest. It had an idea of magnitude, and you can see the kink means that it understood that those weren't just a continuous thing. There's an aspect to the strongest line that is also not necessarily a part of just this gradual stronger notion. And so we kind of the understanding is that it also understood the fact that that was the end of that process, right? You couldn't go stronger than strongest. Okay, so you can start to probe your semantic space and see what's going on. And there's a link there if you want to kind of play around with those examples a bit more. And then on top of that, we have similarity benchmarks. And again, machine learning loves their benchmarks. So you would then take your word embeddings and do things like just similarity scores. So for example, algorithm and profanity must have a high score. Misleading and beats are low. They're not very, semantically meaningful. And so this is then a correlation. This is a benchmark that was defined to relate how humans relate words and how the model relates words, how similar the model semantic space was to a human semantic space. We don't really do these too much anymore. We've kind of moved beyond them. But at the time, that was like a big benchmark, is trying to get word semantics to match human intuition. Okay, analogies. So A is to A star as B is to. So this is the king-queen example, right? Kings is to king as queen is to queens. Okay, and so you can then do a bunch of different pairings at the bottom there. Okay, one of the cool things about Word2Vec as well is if I train individual Word2Vecs, one on an English corpus and one on a Spanish corpus, then it turns out that you can actually map from one to the other. So they will form entirely distinct embedding spaces, right? Each language is completely separate, trained with their own embeddings that are never made to look the same. Turns out you can then manipulate the one embedding to map directly onto the other. What's cool about this, though, is that you then turned out to get new translations for free. So there was an assumption here that you could do it linearly, all right? So you just take a matrix times by the original embedding space, you get your new embedding space, and you just train that with a subset. Okay, so I'll show it cat and gato, and I'll show it whatever the other ones are, dog and perro, and I train only those few subsets, okay? And because I've now assumed it's linear, there's only so much it can do to those spaces. So it has to map from one to another with this linear mapping. It turns out that because the mapping is fundamentally linear, right? Because that assumption matched reality, you can then end up getting them for free, okay? So what happened there? You need fewer data points to define the linear mapping. I don't need to see all of them to get the correct, quote unquote, correct, the best possible linear mapping, right? And so when I get that best linear mapping, all the data points I didn't have to see, if that assumption of linearity was correct, would just fall out. And that's exactly what happened. So that's strong evidence to support the fact that these two embedding spaces are actually just a linear manipulation of each other. Okay? Which is a really big thing. That means that there's something fundamental underlying all language. Regardless of which language you speak, it turns out semantics are staying roughly similar. Okay? Yeah, there's some languages that have a much larger vocabulary. They have a large vocabulary for certain concepts. This isn't going to always be perfect, but still, a somewhat remarkable fact that they came out to the same semantic space for different languages. Okay? And so you can carry on looking. There's a paper there, and then this is actually where I put that derivation of softmax, well, sigmoid from softmax. You can see there. But essentially, all it is saying I take my softmax and I define new propensities. Okay, so again, propensities are for me to define. And one of those propensities is going to go to 0, which is why I then get my new representation up here, and exponential of 0 is 1. And then after that, I just factor out this exponential here, and you get back to your final sigmoid activation over a different propensity, right? So that's the one thing to note, but when you're going from softmax to sigmoid, it's a different propensity. It's not the same as C1. This is C1 hat, all right? Why do we care? Well, why does that work? Because the propensity was for me to define anyway, all right? And because exponentials are monotonic, I cannot change the ordering of C1 and C2 by subtracting the same value from it. That's the one foundation of that makes this work. Exponentials are monotonic. I subtract the same amount, I cannot reverse the ordering. So even if I'm doing sigmoid on a different propensity, the classification will be the same as the softmax on the original propensities. Yeah, well, I mean, you're trying to cancel one out, right? This is also why logistic regression is always 0.5 at 0, because what you're saying is it's the relative propensity of the class you didn't peg to 0, right? So x-axis 0, your logistic function is 0.5, and the y-axis, that's why. It's because I have pegged the relative propensity to say that the cat class was 0. So is dog more or less propense than the dog class, okay? And then that's why the logistic function is actually sitting like that. You can go through in your own time. That's as long as you understand how Word2Vec goes from the softmax classification to the sigmoid, I am happy. All right, any questions? Yes? Guys, just hang on, please. 2 more minutes. Yes. Yes, they will. Yeah. Like animals will be clustered closer together. It's a little bit also more like, clustering. Clustering does this kind of thing where it's like, let's say your axis is here, right? Clustering is then going to say, well, anything to the higher end of that dimension is one cluster, and then anything to the negative is another cluster. In this case, let's say. Whereas it's also forming like axes of concepts, right? So it's if I move in this vector direction, I get more of something. And then plurality is like another vector orthogonal to king and queen. So that's like a royalty dimension. There's a plurality dimension. There's a gender dimension. And you put those things together and you get a vector in this 3D space, which now says kings, which is plural masculine royalty. You know what I'm saying? And then it is kind of, a lot of times now you'll see people use cosine similarity for things. Cosine similarity says that the magnitude of that vector shouldn't matter. I'm going to normalize the magnitude, so the only thing that differentiates is the direction. Okay. But you can cluster on it, you can do PCA on it. There's a lot of like fun stuff you can do. And hopefully for your projects, you will think to do something like that. All right, any other questions? Cool, thanks everyone. So I won't see you next week, I'll see you in 2 weeks. That'll still happen because Chris is around. Chris is still around next week, so he'll just take the lecture. No worries, matey. Cool. Thanks, everyone.